Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to discuss vector addition. So in this topic we will define vector addition, look at the geometric interpretation, consider the conceptual interpretation of vector addition, describe using vectors for changes in position, and consider adding multiple vectors together, and then make some further observations. Given the two vectors u and v, we will define the sum of these two vectors, and we will denote this as u plus v, as follows. U plus v is equal to that vector that adds the first components of each of the two vectors, and the second component is equal to the sum of the second components of each of the two vectors. Easy enough. So basically we just add the first entries and we add the second entries. So for example, if u is equal to the vector on the left and v is equal to the vector on the right, then the sum of the two vectors is just the sum of the first two entries and the sum of the second two entries, giving the vector 10.06 and 6.99. Similarly, here we see that 57.91 is indeed 57.23 plus 0.68, and negative 14.66 is negative 14.92 plus 0.26. Here we see that negative 529.81 plus negative 0.92 is negative 530.73, and 45.09 plus negative 0.81 is 44.28. Now let's look at a geometric interpretation. Here we see two vectors. U is 1.8, 0.4, and V is at the location negative 0.9, 1.1. If we add these two vectors together, we get the vector 0.9, 1.5. To interpret this, you can visualize this sum by putting the tail of the vector v at the head of the vector u. So here we can see the vector u, and from u we move up and to the left in the direction of the vector v. Alternatively, we see that we can also interpret the sum u plus v as starting with the vector v and adding to that vector the vector u. Now, let's consider some conceptual interpretations. We use real numbers at all times in the real world. However, in some cases, if we use real numbers incorrectly, the results are nonsensical. Suppose we have these players here playing tug-of-war. We have players A and D. Player A is at negative 5.9 meters and player D is at 2.2. The origin is placed at the initial start of the game. It is nonsensical to add these two locations. It doesn't mean anything to add negative 5.8 and 2.2 to get negative 3.6. You do not add absolute locations. Suppose now the rope has moved 1.4 meters to the left, or it's moved negative 1.4 meters. We can now change the locations of each of the players, assuming they're still holding the rope in the same location, by adding that amount or that change to each of the locations. So now player A is at negative 1.58 meters plus negative 1.4 meters, which is now negative 6.1 meters. And player D is at 2.2 meters plus negative 1.4 meters, which is now 0.8 meters. So it makes sense to add two real numbers if one was a location and the other is a change in that location. Similarly, let's suppose that we start at the University of Waterloo. So the University of Waterloo is at this location, and we interpreted this as negative 80 0.54 degrees east, or 80 degrees 0.54 west, and 43.47 degrees north. If we were now to move 0.9 degrees east and 0.2 degrees north, then our new position would be at the Elora Gorge, which would be the sum of these two vectors. The first is a location, the second vector is a change in the location, and the result is a new location. But again, it's just the sum of two vectors. Now, important to remember, we're assuming, I know that degrees and latitude and longitude assume the Earth is a sphere, so it's only an approximation. I'm only using this as an approximation, and so it's not a perfect example, but it's not bad either. Once again, it also makes absolutely no sense to add locations. So for example, here, if I add the vector that describes the location of Waterloo and the vector that describes the location of Elora Gorge, the result is nonsensical. You cannot add absolute locations and make any sense out of it. Now, suppose you started at the University of Waterloo and in the first hour you moved 0.09 degrees east and 0.2 degrees north. Then in the next hour you moved 0.12 degrees west and negative 0.18 degrees north, or 0.18 south. You can sum up your total movement in those 2 hours by summing up those two vectors. So after the 2 hours, your total change was just negative 0.03 degrees east and 0.02 degrees north. Thus, relative to the University of Waterloo, you now moved after 2 hours to this new location. Now, this happens to be Laurel Creek Conservation Area, but that's incidental. Now, let's look at an actual example where we're adding numerous vectors. That's a little bit simpler. Here, u is negative 1.8, negative 0.7. Now, from our geometric interpretation, let us assume we make a sequence of moves. So here we move 0.3 to the right, 0.5 down. Then we move 0.1 to the right, 0.3 up, 0.5 to the right, 0.2 down, and then 0.3 to the left, 0.6 up. We can calculate our final position simply by adding each of these change vectors to u. And so if we add all of these vectors up, we get the vector negative 0.6, negative 0.5. That is our new location. Thus, what we are doing is we are starting with a vector u geometrically. We're adding to that the vector v1. To that result, we are adding the vector v2, then adding v3, and finally adding the vector v4. And this gives us our final location, which is at negative 0.6, negative 0.5. Now, one interesting thing, let's remember with real numbers. Remember, with real numbers, it doesn't matter if you add x plus y or y plus x. 3.7 plus 1.2 is the same as 1.2 plus 3.7. Similarly, if I am adding three numbers, it doesn't matter whether or not I add the first two numbers initially and then add the third number, or add the second and third number and then add to that the first number. The consequence of these two properties means that I can add any n real numbers together in any order, and I'm always going to get the exact same answer. Vectors have the exact same property. It doesn't matter how you add all of these vectors up, you're always going to get the same answer. It's always going to equal that final result. So, for the vectors we saw before, it doesn't matter if you add them v1, v2, v3, v4, or v4, v2, v3, v1, you end up in the same location. You don't even have to add u first. Here we've completely reordered them, but notice that the sum of the vectors always ends up in the exact same location. So in this topic, we've introduced the concept of adding of two-dimensional vectors, or we can add more than just two such vectors. All we do is add each of the two components separately. Now, it doesn't always make sense to add two vectors together. If the two vectors represent locations, their sum doesn't mean anything. However, vectors may represent locations, they may represent movements in locations, they can also represent accelerations and other concepts as well. Multiple vectors can be added together, and the ordering in which those vectors are added doesn't matter. Here are some references: Acknowledgments, the colophon, and a disclaimer. Cheers!